Hi, welcome to Concepts of Chemical Bonding. Let's review some really basic information about chemical bonds that we talked about in the first year of chemistry. First, there are three basic types of bonds. One is ionic, which are electrostatic attraction, positive and negative ions, to make things like the magnesium oxide, potassium dichromate, etc., that you might see here in this picture. There's covalent bonding, which is sharing of electrons, which makes molecules primarily from non-metals, sulfur, sucrose, bromine, wide range of chemicals. And then there's metallic bonding, which bonds metal atoms together in pure elements or in alloys. And they bond by sharing electrons between several atoms by using delocalized electrons. Let's focus first on ionic bonding. We just finished a chapter looking at trends on the periodic table. And bonding, chapter 8, measured to indicate how much energy it takes to remove electrons. Let's do a quick review of different kinds of chemical bonds. 459 kilojoules we have ionic, per mole to remove electrostatic attraction between ions, such as that is magnesium oxide, potassium dichromate, ionization oxide, all with metals and nonmetals. Covalent bonds. Then there's another number in a trend we looked at that metal measures atoms typically. That 349 kilojoules per mole, which hold metals together and alloys together. You give chlorine and electron. They're sharing delocalized electrons need to happen when you make sodium chloride. That is called electron affinity. Okay. Now, we looked at some trends in the last chapter. This is a very had to do with electrons being added or taken away. And if we look at those numbers, for instance, taking an electron away from 459 kilojoules to remove electrons from sodium, that doesn't really account for the energy released, the huge energy released when you make sodium chloride. Ionization energy here in the pictures. So what's not accounted for? And chlorine, well, not only do the electrons need to move, in ionic bonding, but we have to talk about, we have to take into account that there's an energy released or absorbed when the ions are attracted to each other. Now, if you think about those together, that's a net absorption of energy. So, and if you're measuring lattice energy, you're strictly measuring the energy required sodium chloride is made. Separate. Well, there's something missing. Solid ionic compound into its gaseous ions, and that is the attraction being between the ions once the ions are made. So the opposite of that, they release a lot of energy when they come together. Doing it in the reverse direction so much more stable for them to be the ions connected together. That's a release of energy, whereas pulling them apart would be an absorption. So this is called lattice energy, and as it's measured, it gets to the energy required to completely use the same idea of solid ionic compound, which we talked about earlier when we looked at photoelectric spectroscopy. This is the opposite of what I just talked about, but it's the Coulomb's law amount of energy, just the energy in an opposite attraction between two different charges. So the energy we're talking about, the ions coming together. So if we look at lattice energy for various amount of energy with a different sign, we can notice that there's needed to take them apart. A difference in their charge on the dictated by Coulomb's law, which we saw recently when we were talking about all of these ions in this which we got two charges multiplied together divided by the distance between those charges, minus one ion. Sorry about that. Energy involved. In this column on the right, we've got lattice energy and minus increases with the charge on the ions. So if you look in this chart, lithium, fluorine, all of these are minus one ions. Minus one ion, plus 2 and minus 2 ions, and down here we have a plus 3. Over here we've got plus 2, minus 2 ions, and even a plus 3. Do you see the general trend of how as a charge increases, sure, you can see the lattice energy increases as the charge goes up? That makes sense. There's more of an attraction when you have a bigger charge. For their lattice, there's also going to be an impact. Higher charge, more energy to separate. The size. It also, on the lattice energy, the size of the ion by the size impacts the lattice energy. So if you look at, we can see the trend. Let's look at some of these lithium compounds. In this case, look at as lithium bonds
ions
with
that are
fluoride
the
and
same
chloride and
cation
iodide.
with different anions.
The lattice energy
fluorine,
goes down.
chlorine, iodine are all attached here to
iodine,
a lithium. Fluorine being
is larger,
the smallest,
than fluorine or
and
chlorine.
then chlorine, and then iodine.
So that tells us that as size goes up,
the atoms get bigger, the ions, get bigger, the lattice energy goes down.
The lattice energy,
I guess
goes
if
down.
ions are farther apart.
Does that make sense with respect to Coulomb's law?
Like in Coulomb's law,
Indeed,
there'll be
it
less
does,
energy
because
needed.
there's
the
less energy of attraction between
of the diameter in the in the
All right,
equation.
let's look at this.
So as diameter goes down, the
lattice
complete
energy
process of
goes
going from the elements of sodium and chlorine all the way to sodium chloride.
All right, so let's put it all
the
together
net change
and look at something called the
is a release of energy.
cycle.
As we know, it's an exothermic reaction. Let's go back.
So here's all the steps that are combined into what's called the Born-Haber cycle.
First, the sodium.
This is a complete look at all the energetics of making an ionic compound.
Then,
starting
the chlorine,
with the elements in their
diatomic
normal
molecule
state.
is separated.
So you've got sodium as a solid,
That takes energy.
and chlorine gas.
Then the sodium
and
atom is ionized,
making it balanced
and
by showing
an
it's
electron is removed.
CO2.
That's called the ionization.
So from
energy.
beginning to end, you can see that there's a net
495
release in
kilojoules per
energy to go to sodium chloride solid. But here's
Here,
all the steps we have to go
The
through.
chlorine takes on that
First,
electron,
we have
and
to
it
notice you got to
releases
make
some 300
sodium into a gas.
kilojoules
Takes
energy per mole.
Then the chlorine molecule has to get
So
split.
the net
from
change right
Cl2
now
to
is
Cl.
still positive.
That absorbs energy.
But here's
and
where we
then
get
the sodium
that attraction between
loses
the ions.
its electron. That's
So it's
ionization
the opposite
energy.
of the lattice energy.
Then
the energy
we get
released
some energy
to
back.
make it into the sodium chloride.
The electron
solid
affinity
we know and love on our
is
problem.
accounted for as the
Right.
chlorine.
Quick review of
gains
electron configurations of ions.
chloride.
Sodium
And then
went
this
from
last step
an
here
S1
is the
to
opposite
a noble
of
gas
the lattice
state
energy.
to be stable. Chlorine went from a halogen
So the
to
lattice
a -1
energy
ion
would
to be
be
stable.
taking
came
sodium
together,
chloride and
released all
separating
that
it into
energy.
ions, whereas the opposite is
Okay,
taking
now in
the ions
covalent
and
bonding,
making it into the solid.
rather than sharing,
That is all
transmitting
that
electrons and then being attracted,
exothermic energy.
they are sharing electrons, and there's attractions and repulsions involved in those bonds. So there's attractions between the electrons and the nuclei. There's repulsions between the electrons and repulsions between the nuclei. Those all have to be balanced out. And when they do so, they get closer and closer together, and at the lowest possible distance for the bond is the lowest energy that minimizes the repulsions and the attractions. We can depict these with simple Lewis structures, which we will be practicing in class. These are all single bonded simple molecules with the goal of having everything have an octet. And if not everything can get an octet with single bonds, then you have to do some multiple bonds. So a single bond just indicates that there's one shared pair, two shared pairs in a double bond, and three shared pairs in a triple bond. Here's some Lewis structures: hydrogen, oxygen, nitrogen. Now, those multiple bonds impact the bond distance, just as the attractions and repulsions did. You've got some extra attraction, so when you have multiple bonds, the bond distance decreases. All right. Covalent bonds, because they're often between two different kinds of elements, can often be shared unevenly. And there are two extremes to how they're shared. They can be pure covalent, shared equally in what you might fondly remember as the diatomic elements, labeled, known as Honkelbriefs. Do you remember the Honkelbriefs? Something you're going to need to remember. Or Brinkelhoffs if you prefer. And then there's polar covalent, where one atom has a greater attraction for bonding electrons than the other. They're often depicted with different colors, and the red end of the molecule is usually very electron heavy, and the blue end is electron deficient. If there's a large enough difference, of course, you get ions, and then they make an ionic bond. Okay, electronegativity drives what kind of bond is produced, and even though it is a continuum, there's some values that can help you have an idea of what kind of bond you've got. If you've got a difference in electronegativity, eneg, as I like to call it, of greater than 1.7, and that tends to be metals and nonmetals, then you typically have an ionic bond. If your difference is greater than 0.4 and less than 1.7, then you've typically got a covalent bond, or polar covalent, I should say. And if it's less than 0.4, it's often considered a pure covalent, not enough difference to be important. All right, so when you get polarity, you have something called a bond dipole that can be measured with a dipole moment. It's not something we're going to calculate, but just FYI, you take the charge times the distance between the ions, and that gives you something measured in Debye's, which is a dipole moment. The bigger the dipole moment, the greater the charge difference between the two bonds, or two atoms. And you can see here, as you go from hydrogen bonding with very electronegative fluorine all the way to iodine in the halogen column, you get a less and less polar bond. Iodine's really large, so the bond length is large, and that reduces the dipole moment. Okay, quick review of naming ionic compounds. You start with the metal, end with a nonmetal, and add IDE at the end. Always add IDE unless it's a polyatomic and it's an 8 or an ite. But if it's just two elements, it ends in IDE. You add Roman numerals if an atom has more than one possible charge, and we'll practice that in class. Whereas in molecules, you don't have any Roman numerals, and to indicate the ratio of atoms attached, you use prefixes, such as in oxygen difluoride, di meaning there's two fluorines attached to the oxygen, or dichlorine trioxide. Hydrogen sulfide should probably be written as dihydrogen monosulfide, but historically it's always been hydrogen sulfide, so it's not written that way. All right, quick review on writing Lewis structures. Find the sum of all the valence electrons. If it's an anion, such as in sulfate, 2 minus, oops, let me try that again. SO4 with a 2 minus charge. Then you would add 2 electrons to the total. If it's a positive cation, NH4 plus, you subtract an electron for that ion. So let's just look at this. Nitrogen has 5 valence electrons. Hydrogen has 1 each, and there's 4 of them. That gives you a total of 9, but you have to subtract 1 for the charge, and you get a total of 8 in that Lewis structure. So that's how you count the number of valence electrons. Then you put the central atom as the least electronegative element that isn't hydrogen. Hydrogen can only bond once, so it can't be in the middle. And connect the outer atoms to the central atom because they're going to be bonded, and each of those dashes represent a pair of electrons. Fill the octets of the outer atoms and see if you've used up all the electrons yet. In this case, we started with a need for 26. We used 6 to bond the phosphorus to the chlorines. That left us with 20. We added 18 around the chlorines to give them octets. So we have 2 left over. So we want to look to see if any other atoms need more electrons to make an octet. Looks like the phosphorus does. So if we add the octet to phosphorus, then, oops, we have a complete Lewis structure because we've used up all the electrons and everything has an octet. Okay, if you run out of electrons before everything gets an octet, then you have to double or triple bond. So you take some of the electrons that were unbonded and you share them between the atom that had them with the one who needs them. And in this case, hydrogen cyanide is going to be a triple bond between the carbon and the nitrogen. And now hydrogen has its 2, carbon has 2, 4, 6, 8, and nitrogen has 2, 4, 6, 8. This is a Lewis structure we would draw for ozone. But if you look at an actual structure of ozone that's measured with X-ray crystallography, we find that rather than having the single on one side and a double on the other side bonds, trying to get this complete, that would indicate they'd have different bond lengths. You have equal bond lengths between all of the oxygens, and that the distribution is equal amongst all the atoms. So that leads us to believe that this is a resonance structure in which one Lewis structure can't adequately depict the molecule, that it is something in between. So if you think of the double bond resonating back and forth, and in reality, it's shared amongst all the oxygen atoms. That's what's going on when you see multiple possible Lewis structures that add up to be the same thing. You use multiple structures, resonance structures, to describe the molecule because it's not easy to draw them together. So resonance is just like mixing paints. Blue and yellow make green. 2 different resonance structures can be blended together to give you what is the reality of the structure. Okay. In truth, the electrons that form the second carbon-oxygen bond in the double bonds don't always sit between carbon and oxygen, but can move among the 2 oxygens and the carbon. So as I said, they kind of stay in between the whole set of atoms. The double bond doesn't just go back and forth. Okay, I wanted to mention that on the outline, I just remembered that there's a section for formal charge, which is no longer included in the AP test. So I eliminated that, but I forgot to take it off the chart, off the notes outline. So don't worry about that. Not responsible for formal charge. Okay, so back to resonance. These electrons that are resonance electrons are not localized, but they're more like a metallic bond where they're delocalized. Benzene is a really good example of a resonance structure. So they have alternating single and double bonds between 6 carbons in a ring. Turns out all the bond lengths are equal. And so rather than drawing 2 different structures all the time, this is what you normally see for a benzene ring because it shows that the double bond is distributed. Okay, there's a couple exceptions to the octet rule. 3 types of ions or molecules that don't follow. You might have ions or molecules with an odd number of electrons. You might have some with less than an octet and some with more than an octet. Let's look at a couple examples. Relatively rarely you can get an odd electron. They're very unstable and very reactive, so they don't last very long, but they do exist. So nitrogen oxide, nitrogen monoxide, for example, is one. And it's a resonance structure between these 2 options. Notice how the nitrogen in this case has 7 and the oxygen in this case has 7. Fewer than 8 electrons, that happens with of course, hydrogen, which can only have 2, but also in the case of boron, because boron, when it makes structures, could double bond to give itself an octet, but it only has 3 valence electrons, and being a very small atom, we find that it gives it a negative charge, which it can't handle. But anyway, boron is an exception, and boron tends to be happy with 6 valence electrons rather than 8. So hydrogen and boron are examples where you can get structures with fewer than 8 electrons and be a fairly stable molecule. The lesson is, if filling the octet of the central atom results in a negative charge on the central atom and a positive charge on the more electronegative outer atom, don't fill the octet of the central atom. Well, that has to do with formal charges, so it really only happens with boron, so let's keep it it's simple at that. Okay, more than 8 electrons. Some elements, such as phosphorus and arsenic and sulfur, can be happy with more than 8 electrons. It's allowed to expand the octet of atoms on the 3rd period of the periodic table or below. Presumably, that's because there's d orbitals available for those extra bonds to use, although right now there's a big controversy of whether they're actually involved or not, but it does follow our experience that only atoms from the 3rd energy level and higher can have expanded octets. All right, some more formal charge stuff that you don't have to do. Let's skip those. All right, covalent bond strength. Most simply, the strength of a bond is measured by determining how much energy is required to break that bond. It's called bond enthalpy, and we have looked at this in thermodynamics, so this should also be a bit of a review. For chlorine to chlorine is 242 kilojoules per mole. There's lots of other bond enthalpies, and it varies depending on the type of atom and the number of bonds. Multiple bonds, as you can see, have higher bond enthalpies than single bonds. Average bond enthalpies are positive because bond breaking is an endothermic process. Bond formation is exothermic. Always deserves another repeat. Note the average bond enthalpies are not absolute bond enthalpies. Sometimes they can change a little bit if, say, carbon hydrogen is in methane versus in a bigger molecule, but what's recorded are average. And they can be really useful when you want to know the energetics of a reaction. You can calculate how many electrons break and how many bonds form, and figure out the difference to find the delta H, just as we did in our thermodynamics unit. Hess's law. Energy from the products, and it's a lot like Hess's law. Bond enthalpies of bonds broken minus bonds formed give you the delta H of the reaction. There's one more example. So add up the broken and subtract out, add up the formed and subtract out the broken, and you get the overall delta H. I'm confident you all are very comfortable with this. We can also measure an average bond length for the different bond types. If you look at this, you can see single, double, triple, they get smaller just as is expected. As you go from single to double to triple, multiple bonds brings them in closer.